What's up? I'm so lost. When will the new homework be released? Uh, I was just thinking about that this morning. That's on my to-do list. I gotta get that one out. The maze solving homework. I don't have a firm when it's gonna happen yet. Um, Probably. I don't know if I want to say tonight, but possibly tonight, maybe tomorrow, for the next homework. I gotta get that one out there. QT Bunny, what's up? It'll be maze solving, by the way. So we don't have you don't have what you need to do the next homework anyway at this point. At this point in time, until we get to breadth first search, that's when you're going to learn how to finish the next homework. And we're going to do pathfinding with breadth first search. And your homework is exactly that: find the shortest path using breadth first search. So there's no big rush, but I do want to get it out there. I still like to have them out there as early as possible. Yeah, trying to start the maze. Day one post gen algo. What? Oh, next semester. Yeah, next semester's remote too. Yeah, I don't know what that comment was. Starting remote in a few weeks. I don't know if the online class or the classes that do meet on campus are going remote. Did we hit enough COVID cases or what? I don't know. I haven't been paying attention. I'm fully remote regardless with all my stuff. I haven't been on campus in a long time. How's your feeling about 116 homework 3 results? I mean, they're not great, but at this point in time, I kind of expect that. They weren't great. But most upsetting about the homework 3 results is about half the remaining class who hasn't already resigned, didn't even bother making a submission. Like, at this point, you're either trying or you're not, unfortunately. And most of the class isn't trying. Like, half the class didn't even submit. And a good portion of the ones who did submit just submitted some last minute garbage and didn't even get an extension. It was so bad. Or you submitted and finished your algorithm. I mean, overall the class did horribly, but those of you who are actually trying and taking things seriously, I think generally did pretty well. I didn't see very many submissions where somebody honestly looked like they really tried over a long period of time and actually put in the recommended 20 hours and did all the testing and did everything they were supposed to, and then didn't get the genetic algorithm done. Because I looked through anyone who submitted but didn't get it done. Most of them didn't do any of the testing. I effectively put the pre-homework in the homework document itself. Most of the people who submitted and didn't get the primary objective complete didn't even bother coding up the tests. Most of them submitted the day of the deadline, like just very pitiful effort, which might just be a reflection of this semester just wearing down on everyone. It's wearing down on me too, to the point where I can't even act surprised anymore. I'm like, oh, another homework where the class basically as a whole blew it off. But and I can't really blame people too much. I mean, so many students are so far behind on learning objectives that they're probably at the point where they're cutting their losses on application objectives and just trying to get caught up on lecture questions and focusing on labs and interviews. So I can't really blame them for that. That application objective isn't going to matter if they don't finish their learning objectives. I didn't get an extension on homework 3 because I was having trouble understanding FP. I mean, it sounds about right. If you don't understand the material, if you're not even keeping up with the material, there weren't very many, I don't know. I don't want to talk about specifics. Plus, man, that time flies by. We're almost at start time already. If you don't understand at all how to do the homework, how can you put an honest effort towards it? But most of the people who didn't get extensions didn't even bother coding up the test cases. I gave you a sample test case in the handout code. If you don't even cut and paste that 3 times and write the other 2 test cases, like at that point, that has nothing to do with you understanding FP or not. I don't know if that's your case. I don't know who you are with your screen name, but I did see that often where people weren't even cut and pasting the single point testing objective. Like if you're not even bothering with the testing objectives that it gave you to help you out, I mean, yeah, there were some close calls on extension that I went for extension. Geometry. 2021 spring is remote. I don't know. Oh, the semester isn't fully remote. My courses are going to be remote. I know that much. I think chemistry labs are open, kind of like this semester. Oh, after Thanksgiving, no one's coming back. Oh, I see. Yeah. When will LO2 be up? LO2. So the first round's been up for a while. The updates. I still got to do LO1, LO2, homework 1, updates. I got to update all that stuff. I'm getting there. The priority right now that the deadlines are out, the priority right now is LO3 lab, because we have the makeup lab this Thursday, and I need to get those results out. I believe the TAs are done with their part. I just got to finish processing and then post the grades. But I got to get those out first, so that'll happen before anything else gets updated. Just so you know whether you passed the lab last Thursday or not, so you know if you have to take it this Thursday or not. Yeah, why Wi-Fi? I'll never know the answer to that. I feel like I'll never be able to figure that out. My assumption is that it's somebody else's money they're throwing away. I couldn't imagine using your own money to come to college and then not trying. But there could also be a lot of other reasons. At this point in the semester, they just might be so overwhelmed as well. Yeah. All right, I can't. I'm not gonna be able to catch up on all chat because we gotta get started. Uh, what am I looking at? Here we go. All right, BSTs, blood, sweat, and tears. Yeah. Jay is your favorite homework so far? Good. Jay is a fun one. It's also an open-ended one enough. Like, you have a clear... It's one of the only homeworks I have where you have a clear goal, and it's up to you to figure that out. Figure out how to do it. I give the sample, like, my expected algorithm just to guide you in case you want some guidance. But it's really up to you. Here's your goal. You have to optimize based on this cost function. Go do it. And there's a wide variety of different solutions to be able to handle that problem. So it really lets you be creative. Plus, you get to do something pretty cool. I think genetic algorithm's a neat thing. Even though it's too inefficient to really be useful out there in the world, but it's still a really cool concept. BSTs, let's talk about it. So today's lecture question, I was about to add testing to this. Well, I was doing the homework extensions this morning, and then I got to the lecture question. I'm like, oh yeah, I wanted to add testing to this. And then I just said, screw it. So y'all benefit from that. You don't have to do any testing for this one. I'll be honest with you on that one. So BST, we're going to look at the binary search tree class today. Take that class from the repo, just like we did for 2 of the past 3 lecture questions. Take that class and write a to-list method that returns all the elements in the tree in sorted order. You can take advantage of the structure of a binary search tree to be able to get them in that sorted order. Just some empty code. Let's go. There were a few submissions. I don't know what these students think, but for genetic algorithm, when I was doing the extension decisions, I think 2 or 3 students just submitted the handout code. They tried, but I looked at the code, their submission, and I'm just like, this is just the handout code, bro. Like, what are you doing? This is not an honest effort. So let's talk about what a BST is. And then we can make that lecture question make more sense. I feel like content-wise, this is one of the lighter lectures. BST can be a pretty involved concept, but not really in the way that we'll talk about it in 116. We're not going to get too deep into BSTs, but I will set you up for 250. This is a big lead-in into a big 250 topic. BSTs are a huge topic in 250. So let's define what a BST is, and then talk about a couple algorithms we're going to write a find method and an insert method in these BSTs. So the definition of a BST, which the tree that we saw on Friday was just conveniently set up to be a BST to have these properties hold. That was on purpose. And so let's go over this. Every value in the left subtree of a node stores a value less than that node. So if I have a node, every value in its left subtree, all these values are going to be less than the value of that node. Every value in the right subtree is going to be greater than the value at that node. And this holds for every node, so this node as well. All the values to the left are less than, all the values to the right are greater than, all the values to the left are less than, all the values in the right are greater than. And that's the definition of a BST. And then we have the situation where we have a tie. If a value is identical, so say 5 was in this tree twice, should 5 go to the left or the right, or should it just not be allowed at all? Those are all questions that each specific implementation is going to answer which way to put the ties. If we want to build, one of the common applications of binary search trees like this is to build a set data structure. So here's your 191 reference for the day. If you want to build a set in your code, you want to have a set data structure. In many languages, and if you want to build your own, these are built off of binary search trees because you can't have duplicates. So if you have the structure of a binary search tree, you can easily find efficiently find where the duplicate is, or if it is a duplicate, and then just not allow the duplicates. So when we go to our insert method, we'll write insert, and we'll have this decision that we'll make. Is this a duplicate? And in my implementation, I'm going to push duplicates to the left, just an arbitrary decision. But if you wanted to build a set data structure that doesn't allow duplicates, your insert method just finds that it is a duplicate, that it already exists in the tree, and then doesn't insert it. And you got your functionality for a set. And that's commonly either with binary search trees or hash tables. You can build a set data structure really efficiently. But this is the definition of a binary search tree. These properties, everything to the left is less than, everything to the right is greater than, or more generally, based on some comparator, just like our sorting methods, based on some comparator, we're going to organize the elements of some type in this binary search tree based on that. In the lecture example and in the tree in the previous slide, my type is int and my comparator is less than, to do the standard, the common standard ordering for ints. Yeah, the mistake, we had some interviews sent out for LO2 makeup to students who did get credit for the LO2 interview already. So there was a correction email sent out if that applies to you. That would mean that you have credit for LO2 if that's what the email said. Which if that email that went out today should have said that. Should have said, sorry, that was a mistake. You already have credit for LO2 interview. So this is our class for binary search tree. We're going to have some comparator which defines how this binary search tree is going to compare elements and its type. We're going to store a reference to the root node of the binary search tree, just like we did with stack and in queue. We had a reference to the first node, and in the queue's case, the first and last node in the linked list that we were using to represent those data structures. And we're going to write two methods, insert and find. And that's what we're going to spend the rest of lecture time on today, is defining these two methods. How are we going to insert in a binary search tree, and how are we going to find in a binary search tree? For LO1 reading, there's more makeup opportunities. Corrado, Kataki. But it's you might have already got credit once I process the makeups that have already gone out. But once I update that, we'll see. The last week of lab for any reading, any learning objective reading, the last week of lab you'll be able to make up any and all 5 of them. So at the very least, you're always going to have that last opportunity in the last week of lab, and possibly other opportunities depending on what learning objective it is. So if in your situation you've been studying and now you understand stack and heap, you're always at least going to get that one opportunity. And for that case, you're going to get more. But I want to talk about all the details right now. So we got to talk about some more BST. So once we have these methods implemented and these algorithms implemented, this is how we're going to be able to use a binary search tree. We create a binary search tree with some comparator. I'm just using ints and less than, just using the standard sorting example approach that we use, just sorting numbers in increasing order. So I'm going to create a binary search tree, give the type parameter of int, and the comparator is going to be the less than operator that takes 2 ints. So my comparator, it takes 2 ints and returns true if the first int is less than the second one, false otherwise. That's my comparator. I'm going to get my common ordering from smallest to largest. Then I can call the insert method, and I'm just going to insert some values into this tree. And I can call the find method, which returns the node at which that element appears. So if I call bst.find4, I'm going to get some binary tree node that stores the value 4, whichever one was created when this insert was called. And if that value is not in the tree, it's going to return null. So that's our idea of that's how we're going to use these things. That's what we want to build. And we want to build insert and find. It wasn't code guy. It wasn't half the class resigned and half. We're not down to a quarter of the class. It's not that bad. It is bad, but it's in line with historically any structure of this course. This used to be in Java. There have been changes when it was in Java. There have been changes since after the redesign. The failure rate has been fairly consistent across all those changes, across different faculty members, across different grading structures. We just lose a lot of students in this class. It's about what it comes down to. But it wasn't half resigned, and the remaining half isn't being able to complete the homework assignments. But it is, the numbers are pretty bad. They are discouraging. I would like to see closer to 100% of the students passing. But when you don't even make a submission, there's nothing I can do for you. There's a certain amount of students who just won't take any steps towards success, and unfortunately, I just can't work with that. There's nothing I can do for you. And I do assess the difficulty of the class on a regular basis. I honestly don't think the course is that difficult. It is a lot of work. You do have to put in that minimum of 12 hours a week. I was very serious on day one when I harped on that. You do have to put in time, and many students report that it is a minimum, and many students say, yes, that is a minimum. I spend way more than that on this course. But if you're not willing to put in the time, then you can't pass this class. Java is the OG language. All right. So let's implement these two algorithms. Oh, and especially being online, just look at the viewer count right now. 70 out of 229 that we started with. If you're not even going to listen to me, what can I do to teach you if you won't even listen to the words that I'm saying? What am I supposed to do at that point? And I do ask myself that question a lot. What am I supposed to do? I could require attendance and treat you like children. I am considering 229 is what we started with. I could treat you like children and force you to show up to lecture and watch the lectures, but I just don't want to do that. I want to have more respect for you than that. I don't want to go down that road. But it is something I do consider each semester. Should I require some attendance this semester? Well, it will get those students to at least have the video open. I don't know. Anyway, so let's write the find method and see how to do this. So I need to find a single element in this binary search tree. And this is one of those cases where I'm going to want to write a helper method to use my recursion. I certainly want to use recursion because we're working with trees. Again, my challenge is still out there. If any of these tree algorithms, I'm going to use recursion. I challenge you to use use loops and try to write these without recursion, I guarantee you it's going to be a tougher time. It's going to be a tough algorithm to write without recursion. So I'm going to use recursion, but I need more than just the node that the value that I'm trying to find. So I'm going to write a second method that's going to add a second parameter here, and that kind of helps out with my search. So now I'm writing another method that isn't just saying find the value A, it's also saying this is the node that we're currently searching. So find the value A, and you're currently at this node in the binary tree, the underlying binary tree, disregarding that it's a binary search tree. It does hold that property. Actually, I guess we're not disregarding that. And then starting at the root. So I'm going to say find A starting at the root, and then the root is going to search from that node onward all the way throughout this tree. And we're going to do that recursively. And the reason we do this, writing the helper method in this case, is we want the second parameter to keep track of where we're currently searching, but we don't want everybody calling this method to have to care about that detail. So if somebody's using this method, they just want to say find 4. They don't want to say find 4 starting at the root. We don't want to put that burden on anybody who's using our code. So we're just going to say, you just tell me what you're trying to find, and I'm going to immediately defer to my method that I wrote that actually finds that thing, and I'm going to specify that we're starting at the root. And this came up when we did the recursive lecture questions in the genetic algorithm. Anytime you're expected to use recursion, sometimes the question itself, the lecture question, will be in the format of, this is how people want to use your method. But to write your recursion, you usually needed another parameter. And I wrote some of those questions. I think the first recursive question I wrote wasn't like that on purpose. And then the next ones were set up like factoring. You're probably going to want a helper method that takes extra parameters. So you can continue your search. You can search, like if you have the current value that you're trying to factor as an input, and then recursively call it by dividing that by each factor that you find, and then keep making those recursive calls. You can do that, but the factor method, the top level one, just takes one parameter. So we're doing the same thing here. We're writing a helper method to help with our recursion that takes an extra parameter that takes whatever we want. For genetic algorithm, those of you who finished it found out that it really helps to have a second genetic algorithm method that takes whatever parameters you want. For my solution, I did the generation number. I had a helper method that takes some other things as well, but also the number of generations that it's supposed to iterate over. And then it would run a whole generation and then recursively call itself, decrementing the generation count by 1. And then whatever I say, if I say run for 100 generations, it's going to make 100 recursive calls and then return the best animal after 100 generations. So for example, so same idea, helper method here. So we're searching this node and we're searching for this value A. If that node is null, we didn't find what we're looking for, then just return null. That's the way we're going to indicate that the value was not found. It's not in this BST. If the value we're looking for is less than or comes before this node's value in the ordering defined by this comparator, then we know we need to look to the left based on all the values in the left subtree are going to be less than this node's value. And I'll keep saying less than just because it's easier to say, but by less than I mean according to this comparator comes before the value. So if the value we're looking for is less than the value that we're looking at this node, go to the left, recursively call the find helper. We're still looking for A, but we're going to the left node of this node. We're going to the left and then recursively looking for that value there. If the value we're currently at is less than the value we're looking for, that means that the value we're looking for is strictly greater than the value we're currently at. So we're going to move to the right and make the recursive call to the right. If this is false and this is false, then this node must have, and the node's not null, then this node's value must be exactly A. If A is not less than the node value and the node value is not less than A, they must be equal according to this comparator. Return this node containing that value. So pictorially, you're a little confused on this unit, Trino? Are these all built in? I'm building these methods. These methods exist in Scala code. Like, there's a Scala tree somewhere. I don't show it off in class at all. But, like, there's a Scala tree that has these methods. There's the Scala list, the immutable list that we've been using all semester, that contains the methods that I showed in lecture. But the ones I show in lecture are just ones that I made just to show you how the concept behind it works. This is how we find elements in a linked list. The Scala implementation of the finding in a linked list, that's going to be different. The code is going to look very, very, very different than what I show in class, but it's doing the same. It's following the same idea. So I'm just showing you how these methods work in theory. Like, this is the idea, the concept behind finding something in a linked list. This is the idea behind finding a value in a BST. Any implementation is going to be very different than that. And honestly, if you look at the Scala's BST find method, it's going to be unreadable. You could read it, but it would take you, hours. It would take me hours even, and a lot of Googling to figure out all these different language tricks that they're using. So I build ones that are a lot cleaner, a lot easier to read, and then I show you those in lecture. Because these make good interview questions, by the way. And in the interview, they'll be like, how does find work in a BST? They're not going to care what language or what specific implementation. They're just going to expect you to be able to say, and similarly for LO4 interviews, you'll probably get this question, but I was referring to job interviews at first. They'll just ask you, how's find work in a BST? And you say, well, if we check the root, and if the value's less than it, we move left. If it's greater than, we move right. If it's equal to, we return it, and then do that recursively. And then, the interviewer's happy, and you move on to the next question. You're welcome, Trino. Yeah, thanks, buddy. All right, so yeah, exactly, P. Yeah, we're reinventing the wheel a lot in this and 115, just to show you kind of how did we get to where we are in computer science? How did the software industry get to where we currently are? So we're reinventing the wheel and showing you this is how these things started. Because at some point in time, there was languages with this as their BST find method, and then over the decades, those find methods just morph into these really difficult to read things as they get optimized like crazy and have a lot of nice features built into them. But this is how things were, and then we can build on these and then show you how just basically how these languages do the things that they do. And then regardless if it's Python or C++ or Java or Scala or whatever, they're all going to do these things in one way or another. This is fundamentally what they're doing. Their implementations are just different. So if we want to find this value 4, we start at the root. 4 is less than 5, so we're going to go left. 2 is less than 4, so we're going to go right. 4 is not less than 4, and 4 is not less than 4, so they must equal each other. Return this node. So we return that up the recursion, and the first call gets that node, this node, storing the value 4, which is what it was looking for. Seriously, reinventing the wheel, personally anyway, reinventing the wheel when it comes to computer hardware, I have so much fun with. I wish I had more time to do that kind of stuff. It's absolutely fascinating to see how... my favorite course that I've ever taken, I don't talk about this much, but it was at RIT actually, and we used hardware simulating software, and we built a 4-bit CPU from scratch. I shouldn't say from scratch, but starting with transistors. So, and it was a very difficult project, but so enlightening to see how we go. Like, you always hear computers are just a bunch of transistors, but actually seeing how a computer, a CPU, can be built with a 4-bit instruction set with just resistors. And we started with resistors, and then our first lab was to take resistors and build NAND gates. And then our next one was to use NAND gates and build like flip-flops and etc. And then we used those to start building our ALUs, and just kept building up and up and up, using registers and all the good stuff. And it really opened my eyes to like what a computer actually is. It's really just a pile of switches built with transistors. So yeah, it might be scary in the sense that it is pretty difficult, but I mean, to be honest, our courses at UB don't get that involved anyway. I wish they were. I've tried to push for that before, but so you won't learn as much. But hopefully you still get that eye-opening moment of, wow, this is how computers actually work. It's just a CPU instruction set that's built with a whole bunch of resistors. It was eye-opening for me, at least. All right, so this is how we find, and then this returns up the recursion, and we get that node storing 4. If we ask for a value that's not in the tree, say we ask for 3, we're going to go left, we're going to go right, we're going to go left, we're going to find null, and we're going to return null up the recursion. Oops, my mouse was on the wrong screen, but I was following the nodes. Hopefully you know it's worth doing. If we're looking for 3, we're going to go left, right, left, find null, and return null up the recursion. Oh yeah, Bobby, good point. Was that a question? I missed that question. But each line here is a reference to the next node. So this node, it has a value of 5, a left child storing a reference to this node, and a right child storing a reference to this node. These nodes, the leaf nodes, this has a value of 7, a left child, which is equal to null, and a right child, which is equal to null as well. Yeah, so the lines are references, and they are one-way references. Like this node here doesn't even know that it's being referred to by this node. So I could put my arrows here as well. Would be fairly accurate. So now let's look at insert. Insert's a little more involved, but not too much. It's more code for sure. But we're going to do a similar idea. We're going to effectively run find, except once we find a null value, we're going to replace that with a new node. So our insert, we're going to defer to an insert helper, which has the node that we're currently searching, the node that we're currently looking at, except we have an extra condition here, if the root is null. So if our tree is empty, if it's a brand new tree that we just created, can you prove that with induction? I've been seeing a lot of circles and dots. Yes. I want you to prove the correlation between 191 and 116 using induction. Strong induction. Inductions, and hopefully this is one of the things, maybe I should draw more connections here between 116 and 191. Recursion and induction, it's basically, very similar at the very least, but in my eyes at least, basically the same concept. If you understand one of them, it's going to help you understand the other. You have the base case. This isn't a great example, but the base case, my two base cases kind of split up a little bit here. But you have your base case, that's the same as your base case in your induction. And then the recursive step, the recursive part of your recursive functions are the same idea as the inductive step in your inductive proofs. It's very similar. It's really the same idea. This idea with induction, the induction step is taking you one step closer to infinity, and the recursion step is taking you one step closer to your base case. But with your recursive step, it makes the algorithm work from your base case to infinity, or infinity size input, or whatever your input is measured by. It allows your algorithm to work up until infinity, whatever the input is, or whatever overflows, whatever data structures, whatever. But effectively to infinity, limited by the hardware. Same idea with recursion, or induction. You start at your base case, except we think about it kind of backwards. With induction, we think of starting at our base case and then using the inductive step to go from our base case to the base case plus 1 to the base case plus 2, all the way up to infinity. But it's the same concept. And in fact, when you're proving in 331, if you haven't gotten enough of all this stuff yet, in 331 you'll write recursive algorithms and then prove that they're correct using induction. So that you'll definitely see the connection. If you don't see it yet, you'll see it when you get to 331. Induction and recursion, very, very highly related topics. Please. Yeah, I think that's for the 331 comment. But before my 331 comment, it was I hope that helps you understand. If you understand one of those concepts, at least partially, try to transfer that knowledge over to the other. If recursion kind of makes sense, transfer that over to your inductive proofs in 191. If inductive proofs make sense, try to transfer that knowledge over to recursion. You're learning the same thing. It's the same underlying concept. That idea that we have a base case, and then we show how to go from one step to the next step. And then that just blows up into infinity. Now you can do anything with this, now that you have those two pieces. Really fascinating stuff. All right, so the insert helper, we have this one extra case where if the root's null, if we have an empty binary search tree, we're going to create a new root and we're done. If the root is not null, we're going to start our actual algorithm starting at the root and looking for the place where we need to insert A. So we do that with an insert helper just like we did with find in find helper. We need to insert A, and this is the node we're currently considering as a node to insert this thing. So we're going to run our comparator first. We're going to say, is this node's value less than the value that I'm trying to insert? If it is, then I need to look to the right, because this value is strictly greater than the value at this node. So I need to be thinking to the right subtree. So I'm going to ask the question, is my reference to the right node, right child, null? If it is, I'm done. I'm going to insert this value as the right node of this node that I'm looking at. So I'm going to create a new node, refer to that node in this node's right reference or right child, and I'm done. I hit closing braces. I hit this closing brace, closing brace, closing brace, returns, and returns up the recursion wherever we found this. If the right is not null, so I have to move to the right to maintain the structure of the binary search tree, and right is not null, so I have to make my recursive call until we do find null. So I'm going to make the recursive call, move to the right, repeat the process. If the value I'm inserting is not strictly greater than the node's value, I'm going to look to the left. So my implementation is going to break ties by moving them to the left. So any ties are going to go to the left subtree. So my binary search tree is now every value in the left subtree is less than or equal to the value of that node, and everything in the right subtree is strictly greater than the value in that node. So that's just how I'm arbitrarily breaking ties. This is where we would say, if we wanted a set and we wanted to remove duplicates, we would say else if comparator of a node.value, then look to the left, else do nothing, it's a duplicate, we're not adding it, return up the recursion, we're done here. But I'm going to break ties by moving them to the left. So if the left subtree is null, if there is no left child, we're going to insert it right there. We're done. We found a spot where we can add this new node. Else, recurse, move to the left. So say this is our search tree right before we insert 7. We're going to compare it to the node we're looking at. 7 is greater than 5, so we're going to go to the right. 7 is less than 8, so we're going to go to the left. Left is null, so we found a home for 7. We can create a new node, refer to that node from this node, and we're done. We can return up the recursion, and now we have a BST with that value 7 added to it. And the recursion returns. Any question on find or insert? The in-order traversal of a BST. Ooh, yeah. It is beautiful. So, can we insert new number to that one? Oh, yeah. Yeah, I don't draw bigger slides, or bigger trees, just because they don't fit on the slide. But we could have a tree with 100 elements, 100 values in this thing. Like if we were inserting 6, for example, if I'm understanding your question, if after we insert 7, we want to insert 6, we would go to the right, to the left, to the left. That's null, and we add 6 right here, referred to by this node containing 7. If we want to add 5.5 after that, we would go right, left, 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 and insert it after that node that we had. So now that we have this, what about 9? Sure. So if we insert 9, we're going to go right because 9's greater than 5, right because 9's greater than 8, left because 9's less than 14, and then we find null, so we're going to insert it right here. Any other numbers you want me to add? I can do this all day. Oh yeah, I mean I said 4.5 just because I wanted to get it to the left and left, just because it was a weird case. Yeah, it would break because this if this is built using the code that I showed where I had ints, yeah, that wouldn't work. You would get a type error, the code wouldn't compile. I just wanted I just wanted to go left, and I was out of integers to choose from. Well, if you gave it a function 2x plus 3, well, yeah, we'll get type errors again. Can you add a list instead of values? So we could with either of those questions, the functions or the values. Yes, but I would have to change my type parameter, and I would have to give it a comparator that can compare two functions and compare two lists, depending on how you want them sorted. All right. So in order traversal, just combining a few of the things that we've seen, an in order traversal on a BST will always give you the values in sorted order. This is one of the very nice features of a BST, is it's always going to give you the values in sorted order, just based on combining these definitions. So we're going to visit the left subtree, which contains all the values that are less than that element. Then we're going to visit the element, the value at this node, and then we're going to visit all the values in the right subtree, which are all greater than that element. And then when we're recursing, when we take the fact that that property holds true for every node in the tree, we're going to end up with the sorted order. So when we go to this subtree and we're printing these 3 values, we're going to print the left, then this value, then the right. And since the property holds that the left subtree has to be less than, the right subtree has to be greater than, we're going to end up printing all these values in sorted order. List that for each. Is that giving anything away? I don't know if that's giving it away. Not giving away the lecture question anyway. I mean, the lecture question, here, I'll give it away right now. Not with code, but you do an in-order traversal and add everything to a list. So you'll need a helper method, so you can have an extra parameter, which is the list. Or if you can append to the list as you're going up. Actually, I don't think that one works. The lecture question is converting a binary search tree to a list in sorted order. So you want a helper method that's going to take a list and then append to that list during the recursive calls while you're making those recursive calls. So append, recursive call on the left subtree, prepend all those elements to the list, recursive call on the right side, append to the end of the list with those values, get this value right in the middle, and then return. Yeah, you can try yield too. You can do it however you want. Yield's a bit trickier though. Yield implies you're using a loop. Recursion, since we're using trees, you should be thinking recursion. So there's one big problem with BST as we've shown them today. So no language, and this is a good example of why I don't use code from the languages or any actual implementations, because they're actually severely more complex than what I just showed you. What I just showed you will not be used in practice ever, anywhere. It's horrible. It's horribly inefficient, I should say. So there's one huge problem here. If our BST is balanced, everything I just showed you is really nice. You're going to get O of log n performance on inserts. You're going to get O of log n performance on find. And just by combining these, if I have n elements in any order and I add them all to a binary search tree and then call an in-order traversal on it, I've effectively sorted in n log n, because insert, it was a log n, the traversal is a linear runtime, and I have n elements. I'm going to get an n log n sorting algorithm without using merge sort or any other n log n sorting algorithm. And it actually has an advantage over merge sort in that it can maintain a sorted order as the tree is growing and shrinking. We didn't talk about delete, but we can delete in log n as well. So we maintain that sorted order even as new elements are being added. We can't do that with arrays or linked lists. If we tried to do that with like merge sort, every time we add an element, we'd have to call merge sort again. Now, inserting elements is going to be an n log n runtime operation, but this can maintain that sorted order, adding a new element in log n time, and still maintaining that sorted order. So this is one of the big advantages of BSTs. If you have a data structure that maintains sorted order, it's almost certainly going to be based on a binary search tree. If there's one built into your language and you're using, a sorted list that always is sorted based on some comparator, it's going to be built on a BST in most cases, unless there's something fancy out there, some new cutting edge stuff that they're using. Probably not. Probably a BST. And you can't do that with our arrays or linked lists, because you're going to get some O of n operations. But this only works when the tree is balanced, meaning that the number of elements, the number of nodes in the left subtree and right subtrees are at least roughly the same. Fully perfectly balanced means they're identical number of elements. But with the implementations that we saw, we don't get these properties. Oh, I forgot to make a Thanos reference there. I should have. Perfectly balanced is all things should be. So our binary search tree should be perfectly balanced. But they're not always. So with our implementation, let's say that we inserted these same elements that we saw all lecture, but inserted them in this order, in sorted order. We insert -3. The root is null, so we just create a new root. We insert 2. That's greater than -3, so we put that in the right subchild. 4, greater than -3, greater than 2, insert 4 here. 5, greater than -3, greater than 2, greater than 4, insert it here when we reach null. 8, same thing. Oops, that should say 7 then 8. I don't know why that says that. So 7 should be the next one. We reach null, add 7. 8, we reach null, add 8. 14, greater than. This tree is not balanced if we add these in sorted order. Yeah, that's actually that is canon, that's backstory not too many people know about, but Thanos was actually so mad about unbalanced binary search trees being O of n that he just had to take care of that. He had to do something about it. He was the only one willing to make the sacrifice to get these binary search trees down to log n. He did what no one else could. So we have this structure which looks a hell of a lot like a linked list at this point. And here we have O of n insert, O of n find. We don't have that nice log n property because we don't have a balanced tree anymore. And this is what we can get with the implementation that we saw. It's horrible. We wouldn't actually use it. So our goal is to keep our tree balanced and still be able to insert in log n. So even when we have that situation we just saw, we should be balancing the tree as we go, something we call self-balancing binary search trees. As we insert an element, if that element is going to imbalance the tree, we need to fix that and restructure the tree, sometimes changing the root, to be able to get that tree back to at least close to balanced. And then we can also remove nodes. We didn't see a remove algorithm, but we could remove nodes and maintain the sorted order and also maintain the balance of the tree is another challenge. And then deciding how to do duplicates, whatever we want to do there. So for BSTs, we're done for 116, but these are the kinds of questions you can expect to answer in CSE 250. You're going to see AVL trees and red-black trees, which will get these properties of maintaining the balance even when you insert the elements in a way that should break the balance, and also maintain, fixing these trees in log n time for your inserts and deletes. So there's a lot of stuff there. But for BSTs, if I show you a picture of a BST or some code for a BST, and you can find elements and explain to your interviewer how elements are found, it's less than, so it goes left. It's greater than, so it goes right. At that level, and be able to inserts basically find, except when you find a null value, that's when you insert the thing. That's when you insert the value, and you have to decide how ties are broken. I broke ties arbitrarily by going to the left, but if you have a different answer during your interview, as long as you explain it well and why, that'd be fine. Thanos is responsible for the 50% pass rate. It's a little higher than 50%. Give yourself some credit. But it is, the failure rate is pretty high. Why do trees have colors? That is a good question. I don't know. AVL trees don't, though. This interview will be tougher than the rest? I don't know, maybe. Yeah, there's no tests for this one. If there's no tests, any empty code would be passing the grader. That is absolutely false. So what for your primary objective does not pass all tests, or lecture question does not pass all tests, whatever, that line there, that's telling you how your lecture question did on my tests. So I run whenever there's tests required, I run your tests like you're talking about, but I also have my own tests on Autolab that are hidden from you. I run those tests against your code, and that's what gives you the, that's one of the things that gives you the one or not. You have to have all of those to get the ones for a lecture question. But I'm still running my tests on this lecture question. You just don't have to write your own tests. I mean, you still should. It'll help you if you're struggling to write the code. It's just not a requirement today. And look, I almost started on time, and I ended up finishing with time left. With 2 minutes left. And I went on some tangents. I guess we didn't have too much content in that lecture. Hopefully it was a little bit of a slowdown. Is there a way in the IDE to visualize these trees? Ooh, that's a good question. Let's do that. There's always a way to do anything, is the general answer to that. If there isn't a way to do something, you can write software to do it. Is the overall super general answer for that. But, hey, look, I already got my breakpoint set. Sample 1. Let's run this in the debugger. probably did this exact same thing with the same breakpoint last semester. So when I have my BST is going to store a reference to its root node. So this is the same code that I showed on the slide. I have my comparator. So I have some comparator. That's a function. That's just a less than function in this case. I have my BST, which is going to store a reference to the root and know its comparator. The root is a binary tree node, which has a value and a left and right node, a reference to a left and right node. So I have my BST, which has a reference to the root node, which stores the value 5. When I inserted 2, I went to the left of that. So my left reference is going to have that node, a node with value 2. I inserted 8 after that. So I looked at 5 and then went to the right and inserted 8. We have 4, which started at 5, went to the left, found 2, went to the right, and inserted 4. We're inserting 7, so we started at the root, went to the right, found 8, went to the left, and inserted 7. 14, we went to 8 and went to the right. And -3, we went to 2 and went to the left. And then all these nodes have left and right of null and null. So there we can visualize our tree. And if we step through this, we can look at the find method, which is going to start at the root, check if the root's null. It's storing the value 5. So we're going to compare. Does 14 come before 5? No, it doesn't. Does 5 come before 14? Yes, it does. So we're going to recursively call on the right node, which is this node at 647. So with at 647 being the current node that we're looking at, and storing the value 8, we're going to do the same comparisons. Is 14 less than 8, or does it come before 8? No. Does it come after 8? Yes. Recursive call on 8's right subtree, which is at 653, storing the value 14. That recursive call, 14, we're looking for 14. The value's 14. The children are null and null. Does 14 come before 14? No. Does 14 come before 14? No. So we hit our else, and we return this node at 653. And we return that up the recursion, up all our stack frames here that are waiting on those recursive calls. Return, 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 and node is that at 653, a reference to that node in the tree, which is that exact same node. This is all by reference. So it's that exact same node that stores that value 14. So yes, you can visualize these trees. I mean, you can't visualize. It won't be like the images on the slide. That's why the slides exist, to give you that visual. But you can go through all the references and see how these trees are built. And if you're still looking for more practice with the debugger, I think that's a fantastic way to do that. Set that same breakpoint, or better yet, change this around. Set your breakpoint like this, run it in the debugger, follow all the references, and then draw the tree on a sheet of paper. Would be excellent practice. And then once you do that and you get practice going from the debugger to a tree, then get different values again, shuffle all these around or whatever. And just looking at your code, try to draw the BST, because you can guarantee you're going to see that on your lab next week. Draw it from the inserts. Draw the binary search tree based on how, when they're going to look left, when they're going to look right. And then check your work in the debugger. So you can generate your own lab questions this way, just by doing random inserts, drawing the tree that you think will happen, and then verifying in the debugger that you actually do, in fact, get that tree. Either for today's lecture question, either way, they're unrelated, so they're not building on each other. So P, you can start at this lecture question with a fresh one, or use your other one. It's not going to matter either way. What was? And I'm blanking on. I know they're not related, but I am blanking on exactly what that one was. Oh yeah, the expression trees. And they're very similar. They're both in-order traversals, just variations of in-order traversals. But you don't need them. You can use a fresh start. Let me get chat on screen so you can see what I'm looking at. Trying to figure out where I left off and what I missed. I remember saying trees have colors. This interview. I don't know if this interview will be tougher than the rest. I think interview 1 is actually pretty tough. Explaining stack and heap in an interview. I don't know. Maybe this one will be. Do we have to create test packages and pass? There's no tests. Yeah, there's no tests. Oh no, I did. I talked about that. I went too far back. Yeah, this is what prompted me to go to IntelliJ, so let's pick up there. Do it small. Yeah, you don't have to write tests for this one. Greetings from Bulgaria. What's up, Zarbubba? It's here for time management. I wish my students had more time management skills. But say la vie. It's tough because I usually say this at least once a semester to every class, and I think the students hate it every time I say it, but my job would be a lot easier if y'all would do what you're supposed to do, and I could actually build out my courses more. I would have more time to like revise my slides and focus on improving quality. But seriously, do like grading decisions. If I go like the extensions today, if I go in there and just everybody has credit for the homework already, there's no decisions I have to make. Like I'm done. That's one thing that I don't even have to do. The interviews, if everybody passed their interview the first time, we wouldn't have to do re-interviews. We wouldn't have to do makeup labs if y'all just got your labs done. We could actually do a lot more. But I had to spend a lot of time, and the TAs had to spend a lot of time on students who don't have good time management skills yet. Hopefully they'll get good time management skills. And to be fair, why should you have good time management skills when all through high school you can just blow off everything, and the teachers are pretty much required to force you to pass, even if you didn't learn what you're supposed to learn. So it's very easy to learn that, and even if you're not a slacker, when you see your friends doing half as much work as you and still getting through and getting shoved to the next grade, eventually you're going to get discouraged, and if you don't see the intrinsic value in your education, it's easy to start slacking off yourself. And then you get in college and it's like, hey, if you fail, you fail. Like, we're not going to help you. We're not going to hold your hand and baby you all the way through college. Like, sink or swim, figure it out. And it's a big culture shock. Like, it's hard to adjust to. And if you're only, you're only in a second semester course, I can't really expect you to have those skills yet. Which is why I'm always torn. That's why lecture questions exist. Because I know you're not going to study on your own. Most of you. Some of you will. But most of you won't study on your own without the lecture questions. I need something pushing you and making sure that you know whether you're on track or not. I can't just throw you into the homeworks. Anyway, I could talk forever about that comment. I'm skipping that one. I'm cutting that one short. Where I was distracting you. Yeah, there's always a way. There's my visualize the trees comment. There's always a way. That's why you're here, right? You can get a computer to do whatever you want. Anything. Yeah, if you only miss GA, you can still get an A-, yeah. if you get everything else. And yes, it is in the syllabus. Gorilla MILF. Oh boy. Yeah, you can, if you want to resubmit. Yeah, if you already have if you got the 1 for code today, even if you resubmit and you don't get a 1 and you break everything, it's fine because it's already in the gradebook that you already have credit for the code portion of that application objective. So yeah, go nuts. There's also an expansion objective if you want to keep working on that. Go for that too. Knock yourself out. And that one I skipped ahead and answered. Yeah, you could get an expansion objective for homework that you did not get credit for. Yeah. You can still. I'll still give credit for the expansion objective. No student has ever done this before because you got to do. You still have to do the original assignment just to get to where you can start the expansion, and without getting credit for, there's probably something else you could be doing that you'll get full credit for. And if most students who are actually interested in the expansion probably just did the original assignment before the deadline anyway. Yeah, I don't think I made that clear to my TAs. I don't think they'd have a good answer for you. But yeah, I'll allow it. I don't see why not. Debugger is a lifesaver. I can't even count how many hours the debuggers have saved me. That was a great day in my life when I figured out what a debugger is and how to use it. I wish I was shown the debugger in 116. I don't think I seen the debugger until I was in grad school, I believe. I was just hanging out with a fellow student, and they're like, "Hey, why are you doing it that way with print statements? The debuggers are a thing, right?" I'm like, "Oh, really?" And they showed me a little bit, and then I googled some tutorials to fill in the rest, and I'm like, "Holy crap, this thing is great." I really wish I knew about that all along. So I try to show it in lecture to benefit all of you, and that you don't have to go through the pain I went through. Could we do this along with Plotly? That'd be interesting. I mean, I'm not going to stop you. Could I do that in lecture? Like this lecture could benefit from a lot of good visuals. Someday maybe I could do that during lecture, and even give you the Plotly. And there are tools, by the way. There are tools online. If you do visualize BST, I mean, you'll get what you're asking for too. Visualize BST, binary search tree visualization. Insert 5, insert 20, insert 50. Oh my goodness, this is beautiful. Why would I have to build it? It already exists. And let's get one to the left of 50. Let's do 30. Yeah, there you go. Just, internet's your friend. Let's find 29. Found. Let's find 8. Not found. Everything you could ever ask for, right there. So yeah, given that exists, I probably wouldn't build a tool. I forgot where I was. Plotly. Yeah. I mean, this is true with everything. Who wrote Scala? Who wrote Python? I don't even know who the people are. They get no recognition but they gave us probably millions. It's got to be at least millions for each language. Millions of lines of code for free. Like, zero recognition, quite possibly zero money. I mean, what language have you ever paid for? They developed compilers and interpreters and all kinds of tools, debuggers, IDEs for that matter. I mean, I guess our IDE, IntelliJ Professional, at least you would have to pay without the education license. So they do have a business model. But like, what's Python's business model? To be honest, I don't even know. Maybe they do monetize somehow, but I don't think they do. Think of just how much code you use for free. It's phenomenal. I don't think that exists in any other industry, that we just have so many just free tools. It's wild. All of Linux and the GNU licensed software, so much open source software. You don't see that in any other industry, as far as I'm aware. Maybe there are, but yeah, that was the first computer bug. It was an actual bug, literal bug in I believe a vacuum tube, found by Grace Hopper, I believe. It's a bit of history I remember. You gotta give me a little more info there. If you tell me the name of the failing test and try to give you a hint real quick. But if you're that close, we'll probably overlook it. But then you do have to rely on that decision. Your fate's in our hands, and mine and the TA's. If you take a hint and get it done, then there's no question we're going to give it to you. Preaching to the choir. That's most things that I say. Because only the choir listens to me. Like, the people who need to hear, especially when I give the more stern warnings, and the time management must have been what I was saying here, is the people who need to hear it aren't listening to me. Like, if I say, if the class would just listen to lectures and show up to lectures, you'd be doing a lot better. Yeah, but the people who need to hear it, by definition, won't hear it, or at least not in time. They might hear it right, during the last week of class when they're trying to do all their makeup LOs all in one Thursday, but they won't hear it in time. Or trying to do all their lecture questions December 11th, or December 9th. Is it 11th or 9th? 11th, December 11th. They're trying to do all their lecture questions in one day. Yeah. They're probably going to listen to all those. They're going to be watching through all the old videos, and then every video I have this one little, minute or two where I go on a little rant, and they're going to be like, oh man, I wish I listened to that. Professor not equal parent. And unfortunately in high school, they kind of, you know what, I'm not going on that rant. In high school, they are expected to be more of parents. There's a lot of, I will go down this road a little bit. There's a lot of things that, at least in my opinion, that parents should be doing that they not by and large, but there are certain students where their parents just don't do what they're supposed to be doing. They're not being parents. And then they just expect the teachers to be parents. And then the administration usually sides with the parents. If I can say that without being too confusing and without being too abstract there. Where the teachers are just expected, like if a student's failing, it's always the teacher's fault, especially in high school and K through 12. And they have to take all the heat, even though, you give a student homework and they just don't do it, and the parents don't make them do their homework or anything. Like, what are you supposed to do? And unfortunately, it's, No Child Left Behind. Just shove them into the next grade, even though they don't know what they're supposed to know. So teachers don't equal parents either, but unfortunately, they're sometimes put in a position where they kind of have to do some parenting, which is sad. Sad for the children. I certainly won't act like a parent in this. I'm going to say, here's the deadline, here's your homework, here's what you're supposed to do. Oh, you didn't do it, here's your F. I'll see you next semester. You gotta be responsible. Again, preaching to the choir. 2:59. I gotta. Maybe. I mean, to be honest, I won't find the time, but it would be nice to cover. Maybe during review session. Maybe you can ask the TAs. I don't know. I don't know if they'll have time to cover it either. Do we have expansion in LO4 and LO5? To be honest, I don't remember. I mean, at least one of them I'll try to get an expansion on. I don't remember off the top of my head what I have planned for those.